So I welcome everyone to today's session, especially you, David. Thanks for joining our Julia user group Munich meetup today. I'm very much looking forward to it. As already said, you're welcome to ask questions, everyone. Please use the chat, but you can also raise your voice. And yeah, we will manage and hopefully answer all your questions to your satisfaction. To begin with, some small words about myself. Stefan Sam, you know me, I'm organizing this meetup for a long time. And since recently, I've started my own Julia company. So if you see some benefits of the Julia language in your company, in your project, please feel invited to drop me a line. I'm searching for connections into the industry here and there. Yeah, it would be really helpful to get your help here. Thanks a lot. Today we have David with us, David Sanders. He developed the JuliaIntervals ecosystem with Julia Arithmetics and a couple of more packages. So that's why you're all here. We want to learn more about the intervals in Julia, calculating with sets. What you see today, he developed as the professor of the National University of Mexico. And now he is working with relational AI. Maybe you heard of that too. It's a Julia-based company with some database focus. Okay, David, then stage is yours. I hand over to you. Thank you for being here.
Hi, everybody. So thanks very much to Stefan for the kind invitation to speak at this meeting. Unfortunately, I've never actually been to Munich. I hear it's a very beautiful place and I would love to go, but given the current situation with COVID, etc., who knows when that will be possible. On the other hand, as I was just discussing with Stefan, it gives us the opportunity to do sessions like this. Maybe there are people from all over the world in this session. So, certainly places like JuliaCon have become more inclusive as a result, actually, in many ways. Yeah, so thanks for being here. As Stefan said, I'm going to talk about this project that I've been working on for 8 years now, actually, JuliaIntervals. So I don't have slides exactly. This is designed to be a sort of interactive demo type presentation. So let me just show you, a bit about JuliaIntervals. So JuliaIntervals is a GitHub organization, which is a suite of packages that we have developed for doing interval arithmetic. So the goal of today's session is to, discuss a bit about what interval arithmetic is, what it's useful for, why we should care about it, basically. And so there are quite a few packages now in this organization. And I'll discuss a few of them. I won't talk about all of them. And okay, in particular, one of the things to know is that there is quite good now documentation at this link. So juliaintervals.github.io, just go to that link. And this is the actual documentation. And this was all revised a lot recently by Luca Ferranti. So we've been lucky to have various people join the project over the last few years, a few GSOC students, and then Luca was actually Google Summer of Docs, Google Season of Docs contributor, so he did this nice web page. And so if you go to, you can see that there's a list of the packages and some tutorials and things. If you go to explanations, there are actually, and video resources, there are actually a few videos that I and my collaborator Luis Benet at UNAM, National University of Mexico, he's the other main, let's say, co-founder of this project and main other co-developer. We've given various talks at JuliaCon and other places. And so, for example, in particular, I gave this 4-hour workshop at JuliaCon last year. So if you want more details about what I'm saying today, I go into quite a lot of detail in that workshop. And there's supplementary material, which is basically just a set of Jupyter notebooks. Okay, so if you go to JuliaIntervals, yeah, okay. There's the link to the documentation. So, so JuliaIntervals has quite a few packages now. So there's a list of packages in this documentation, which was done by Luca Ferranti. And this doesn't actually list all the packages. But if you go to explanations, there's a set of video resources. And the first one is this Calculating with Sets workshop that I taught or gave at JuliaCon last year. Well, now 2 years ago, I guess, a year and a half ago, JuliaCon 2020. And there's quite a few Jupyter notebooks that go through that in quite some detail and a quite tutorial kind of way with some exercises, etc. Today, I'd like to just basically mainly do some demos and a bit of live coding to try and sort of explain what interval arithmetic is about and why I care about it and why maybe it might be interesting for you too. So I'm going to start with a demo, which is, okay, so I'm interested in scientific computation. So, any kind of computing that will try and solve some scientific problem. For example, there's an asteroid called Apophis, which may or may not collide with the Earth in 2029. This is actually a real thing. And so currently we can measure where Apophis is. But when we measure it, we can measure its position and its speed or its velocity, but we can only measure those within some range, right? Because we're using certain physical detection, astronomical instruments, etc. And so we have some little range of uncertainty in that information. And then we know the laws of physics that say, okay, the asteroid is going to move because of gravity, the gravitational interaction with the planets and other bodies in the solar system. And the question is, if we follow, we can solve, so we write down some equations that model that system, and then we can solve those equations, which are differential equations and ordinary differential equations, pretty complicated ones, I guess, and we can predict, is the asteroid going to collide with the Earth? Except that we have this uncertainty on the initial state, the initial condition, which basically says that, well, the position is within some little range, and the velocity is also within some little range. And so basically what we would want to do is sort of check for all of those initial conditions, follow the trajectory, which is some curve, and see if that curve is going to collide with the Earth, and then do it for some other little initial condition. So that's the kind of question that we would want to try and answer. So if you think about sort of a lot of scientific problems actually reduce to solving some kind of equation or maybe some inequality. And so let's start with some simple equations and inequalities and see what these methods can enable us to do. And then I'll try and show how that actually works. So first, I just want to show what these can do. So I'm going to be using Julia, of course, because it's really a great language for doing this kind of thing. And I'm going to be using the Pluto notebook, which you may know, because it's a great way to get an easy sort of interactive experience. So I have this, everything was working so well, and now that's the wrong version. Sorry about this. Let me try and change this and see if that's going to actually work. What's going on? I can't edit this. Oh, that's the wrong. Everything was so carefully planned. And then, of course, it all starts going wrong. As soon as there we go. Okay, this is the right notebook. Yeah. There we go. Okay, great. So I have an expression here, and I have like a choice of expression. So let's look at this one. So let's look at a nice simple one. So ax squared plus by minus c squared is greater than d. So that's the kind of typical expression kind of that you might write down in some maybe high school geometry or university class. So maybe we'll just make this an equation to start with, right? So that might be more familiar. So I have these parameters a, b, c, and d. So this is a Julia expression, a piece of Julia code that I'm writing, but then that piece of Julia code is going to get modified somehow. And then what I'm actually doing is converting this into a symbolic expression using the great symbolics.jl package. And so you can see the output here. This is a symbolic expression in this symbolics package. Once I have substituted in for A, B, C, and D, these values that these sliders are giving me. So if I just move this slider a bit, you can see that the expression changes. So I'm moving B here. So B is multiplying this y minus 2 squared. And if I change B, you can see that the value here changes. And then what I'm drawing here is actually what that set looks like. So this is a set in the XY plane. So all of my examples right now are going to be in 2 dimensions. And so I'm interested in the set of values or pairs x, y, which satisfy this equation. So it's some kind of, I have x squared and I have sort of y squared. So it's some kind of quadratic-like thing. And so let's make b positive. And then we see that the answer is this kind of thing. So if you remember from some kind of geometry class, if you took geometry, when I have kind of square things, I should get some kind of conic section. So here we're seeing that it's actually a hyperbola. And as I change b, you can see that I'm, the set of values changes. Now, if you look carefully, if I sort of zoom in a bit, you can see that what I'm drawing here are actually boxes, rectangles. I'm not really drawing a smooth curve. We know that this should be just a curve. But what I'm drawing are rectangles. So why am I doing that? And the answer is that this picture is actually different from most pictures you will see of this object. Mostly, they will just draw a curve. And what that curve represents is some approximation to the set. So they, for example, put in a value of x, and they say, oh, there's 2 possible values of y. I'm going to calculate those using floating point arithmetic, and I'll see that y is, maybe 1.32, and this other y is sort of minus 7.9 or something. But those are approximate values. So when I'm doing calculations with floating point arithmetic, my results are always an approximation. They can be very, very close to the true answer, but they're always, you never quite know. You sort of never quite know if the result is correct or how far away that result is from the true result, etc. And what I'm drawing here is actually, you can think of as being a guaranteed to be correct result. In other words, this rectangle is guaranteed, if you believe that my software works correctly, which, it's difficult to get software to work correctly, so we should always doubt whether it's really working correctly. But let's suppose that it is. Then this rectangle is actually designed so that it definitely contains the correct result. So for each, you can see that it has some little distance in the x, some width in the x direction and some width in the y direction. This is saying that any solution of this equation, in that range of input values of x, the output lies within that little range of values in y. So that is what interval arithmetic is actually able to do for me. It's able to give me a way to enclose the range of a function, basically, the set of output values of a function. And it can guarantee that it does it correctly. And now you can see that, okay, it's a bit annoying. I have these kind of big boxes. I don't want that. Can I get a better approximation? And the answer is yes, I can get a better approximation by changing the size of the boxes. So changing the maximum width of the boxes, I can get a better approximation. And as I change the boxes to be smaller and smaller, I get a better and better approximation. Of course, if I zoom in enough, I'll still see little boxes. And the problem is that if I make the boxes smaller, I have to do more computation. And it probably scales in some nasty way as I decrease the size of the boxes. But basically, you can get as good a solution, as good a result as you want by taking smaller and smaller boxes at the cost of doing more and more calculation.
There's the first question.
Yeah.
Does it deal correctly with the complexity of floating point computation?
Yep.
Like limited precision, the order of operations matters, etc., etc.
Great question. Yeah. So that was basically the original motivation for interval arithmetic, was exactly to sort of deal with all of the rounding errors and mess that you get from floating point calculation. So the answer is yes, it does deal with it correctly, and I'm going to try and show you how and why it's able to. Yeah, so that was sort of the original motivation. And now I would say that, so what does interval arithmetic do? It enables me to actually compute with sets, right? And so in order to deal correctly with the complexity of floating point arithmetic, what do I need to do? I actually need to take little, instead of taking one floating point number, I need to take a little region, a little range of numbers around a particular input. And I want to calculate with all of those all at the same time. And that is exactly what interval arithmetic is designed to do. Yeah, so thanks for the question. Okay, so let's look at some other cool expressions. So instead of equals d, let me change that to less than d. So now I'm drawing all of the points. In blue, I'm drawing all of the points that are inside this set. So now because I have a less than here, whereas before I just had two curves, now I have all of the points in the plane between those two curves. And of course, this is an infinite set of points, uncountable is a very large number of points in here. So what I'm drawing here in blue, let me remove these boxes. I'm claiming this is the set, of all of the points x, y in the plane, well, not in the plane actually, right? Just between -5 and 5 and -5 and 5. Okay, just in this box in the plane, this is all the points that satisfy that inequality. So, of course, since there are an infinite number of points, I can't do an infinite number of computations. So what am I doing? So that let's put the boxes back. And so the answer is I'm splitting up the plane into these rectangular boxes. So what can I do with these boxes? So this blue box here, what I'm saying is I am guaranteeing, interval arithmetic guarantees that all of the points in that box are contained inside this set. So I'm going to call this set a constraint. It's a restriction on the possible values, possible pairs of x and y. So pairs that satisfy this constraint are inside the set, and pairs that don't satisfy it are outside and drawn in white. And if I increase this sort of threshold, this box size, you can see that there's also something else, which are these red or orange boxes. So blue is inside, white is outside, and orange is on the boundary. So orange. What orange means in this case is that I actually don't know. I don't know, for points in those boxes, I don't know whether they're inside or outside. But as I decrease so if I don't know, well, how can I know? Well, I can just make the boxes smaller. And so you can see that I can refine those boxes by proving that some piece is inside and some piece is outside. But there's always going to be this sort of, even, as I refine more and more, I take smaller and smaller boxes, you can see that there are always left some small piece where I don't know. And that's partially due to these questions of floating point arithmetic, and it's partially just because, so what am I doing? You can see, by drawing these boxes, you can see that I'm approximating my complicated set by a union. A union just means, basically a collection of square boxes, rectangular boxes. And you can see that when I have a, kind of diagonal curved line, that's a bad idea, actually, because I need more and more smaller and smaller boxes to approximate that curve using these boxes. But anyway, so there are other things you can do. There are other things that are more sophisticated, where you can use sort of polygons instead of boxes, etc., but they're more complicated. So we're just going to do the simplest thing in this talk, which is just use boxes. But you can see that even with boxes, I can get a pretty good answer. So if I just again remove the boxes again, you can see that, yeah, I see in that kind of pretty smooth curve, I have this little bit of orange where I don't know whether it's inside or outside. Question?
Another question, yes. A question from Lasso.
Yeah.
Here, due to symmetric nature of the problem, these boxes look quite symmetric as well. How things will look like when your regions are asymmetric?
Question. Yeah, so I don't know how to make it more asymmetric. I don't think I can with this particular example. So let's go to a different example. Here's one. So I changed I changed the cube to, it's kind of hard to make nice examples where maybe I'll just add an XY here. So you can see that it's pretty nice because you can just type your expression and see it output. And of course, because it's Pluto, when I type the expression, it immediately gets re-rendered. I don't have to reevaluate anything myself. Okay, so here we have a nice asymmetric thing. So so that's the answer. It just works out what the boxes have to look like. And so one of the things I'm going to show is how you actually do this, right? So you can see that sort of it took, for example, this box here, it seems to have taken, at least maybe it didn't do that exactly, but roughly it took this box here and it sort of removed some portion of the box that it could prove was, inside, and some portion that could prove was outside, and then there's some portion left over and it has to subdivide that. And that's the basic algorithm. And I'll show how that works. Okay, and you can see over here that there's some strange thing going on where there's sort of these boxes that look like they're outside the set in the white, but it can't quite prove that it can actually remove that box. It can't quite prove that everything in that box is outside, and it leaves it as unknown. And so as I refine, as I take smaller and smaller boxes, it will eventually prove that that's outside probably. Okay, so hopefully you're getting a feel for how, what these methods do. And you're probably wondering, how is it possible that this is, how is this even possible? How does this work? Hopefully. So that's the goal, to show what's going on. And so so again, you can see, if I have an equation like this and I'm trying to solve it, for example, I want to solve this thing equals 0. So that is actually the set where, the set of all xy pairs where this expression is 0. But for example, you might want the values where that's 0 and x is equal to 2.5, right? So it's going to be this point and this point. And so that's another thing. So that's like finding roots or zeros of an equation. That's another thing that interval arithmetic is great for doing. And these days, what other scientific problems or what other sort of mathematical, basically what we're doing is mathematics, right? We're doing computational mathematics, and then we can apply that to economics and all kinds of fields. For example, today, one of the main things that I guess a lot of computers are doing all around the world is sort of using neural networks to do machine learning. What is that? It's just optimization. And so it turns out that interval methods can also do optimization. In fact, what they can do that no other methods can do, basically, or almost no other methods, is global optimization. So they can actually prove that you have found the global minimum of a function, the lowest point of a function. That can be, you can actually solve that problem using interval arithmetic, but only if the function is in low dimensions. So we can't actually use it to solve these neural network problems, really. Although, actually, a colleague of mine, Marcelo Forez and Christian Schilling, they're both in the Julia community. They're the authors of the Julia Reach set of packages, which has a lot of intersection with the interval arithmetic kind of ideas. They recently published a preprint where they actually use their more sophisticated methods to try and solve neural network problems. Okay, so that's kind of the overview. So let's jump to, let me show you an example of doing the same thing in 3 dimensions now. So in 3D, because again, we're in Julia, so I can use the beautiful Machi package to do 3D visualization. So here's an example of 3D visualization using Machi. So again, this is an interval, using the same interval technology, right? So basically what I'm doing here is I have this surface in green, that's x equals y cubed. Then the surface in blue is y equals x squared. And then there's a z coordinate in the 3rd dimension. And these blocks here are the intersection of these 2 surfaces. And that's what's called the twisted cubic. It's a famous curve in algebraic geometry. So you can see that I'm drawing it with these, it looks very blocky because I deliberately chose the block size to be high so that you could actually see what's going on. And basically, again, it's a 3-dimensional curve, and I'm enclosing it with these boxes now in 3 dimensions. And you can see that the boxes have, different sizes and different dimensions. And if I decide to make the boxes smaller, I'll get a much better approximation to the actual curve. That's a cute example. And then let's look at another example, if I can find the right terminal, which is always an issue in my life. It's a triply periodic function. So it's it's a function given by, so let's actually open that. I can show you what the function looks like. So it's just this function here. So this is the actual code that I'm running using my package, interval constraint programming. So where is the function? Yeah, the function is this one. So cos x times sine y plus cos y times sine z plus cos z times sine x equals 0. So that's going to give me a surface, and right, I have a constraint that this thing of 3 variables, this function of 3 variables has to be equal to 0. That's going to give me a surface, a 2-dimensional surface in 3 dimensions. And because I have this kind of symmetry where I'm just replacing, I have x, y, and then y, z, and then zx, I'm going to have some kind of symmetry in my surface. And because I have cos and sine, I'm going to have periodicity. So the result is that it yeah, the result is that it looks like this. So this is, this is like, I don't remember how many boxes. It's like 200,000 or 1 million boxes, and because Machi is using OpenGL and whatever, so it's just rotating smoothly in this object. And so again, what is this? These are little tiny boxes. Like, can I zoom in? Oh yeah. I can zoom on, but it doesn't work that well. But you can hopefully see that these are tiny little cubes or cuboids, sort of rectangular boxes in 3 dimensions. And again, this is a guaranteed over approximation. So this is a set of boxes that is guaranteed to contain the surface everywhere. Okay, so that's different from, right? So I was going to show. You can do this kind of calculation, of course, in Mathematica, in Desmos, and other cool systems that have, that are very, very neat in their own way. But most of them cannot do this, this computation where you actually guarantee that what you're seeing is correct, right? So, for example, let me go back to my 2-dimensional. Yeah, somebody said beautiful. Yeah, I agree. I was pretty happy when I saw this for the first time. Let me go back to my, where is it gone? To this. Yeah, so we're going to choose, so this strange function, this is from a paper by a guy called Tupper from like 1996. He was doing this kind of calculation using intervals. And he was interested in just sort of making sure that when you plot a set, you're plotting it correctly. So this is what we're doing here, right? So again, blue is guaranteed to be inside. So here's the function that I'm plotting, or the inequality that I'm plotting. So again, this is going to give me a set, a sort of thick set, and it looks like this. And then I'm going to change it to go from -10 to 10 or something. And so it's thinking. This thing means it's thinking. It's doing this computation, and it's pretty heavy. So that's why it's taking so long. Because it's really generating all these, tiny boxes, and it's proving again what's inside and what's outside, and you get this kind of weird, interesting shape. And then because we're in Pluto, etc., and Julia, I can just replace this 4 by this variable b, which is currently 1.3, and it'll recompute everything, and it looks something different, right? And I'm going to move b a bit, and it'll change the shape again of this thing. So this is quite possibly, nobody's ever seen this picture before. And so what kind of questions can you ask? Well, you can see here that, oh, there we go, that thing separated, right? So are these joined together, or are they, okay, sorry, it's very slow. So I moved the slider a few times, and but you can ask the question, is this piece joined onto this piece? And you can see that in the picture, it looks like it isn't. If you draw it in some other system, you can't guarantee that, right? You don't really know if that's connected to this. But here, because this is, again, guaranteed, you really know that there's this white space in between. You can actually show that this is not connected to this, etc. Okay, so yeah, and then I wanted to show one more cute picture, which is this. So maybe I should decrease the box size. So yeah, so this is this particular crazy function. I think I found that in some paper as well. And it looks like this. And if you type this into Desmos, I don't know if you know, Desmos is this very cool kind of calculator program designed mainly for kind of high school students or even younger, it immediately plots this figure. It's much faster than my software. And then I can just zoom out and you get this crazy checkerboard thing here and this thing here. But you can see that it says this equation contains fine detail that has not been fully resolved. And you can see there's something going wrong here. But you don't really, it actually detected that and reported it to me, but you don't really know what's going on. You don't really know what's right, what's wrong. And so, whereas here, I'm guaranteeing this picture, right? In the sense that I'm telling you exactly where I don't know what's going on, where I do know what's going on. So that's why it's, these methods are so cool. Okay, so let's actually look at how they work. So any questions until now? Okay.
No more questions.
I'm going to make a new notebook. So we just discovered that the developers of Pluto, especially Fons van der Plas, who've done a beautiful job, have a sense of humor, and there's this sort of seasonal snowing background to new Pluto notebooks now, which is quite amusing, but maybe a bit off-putting. Anyway, so what is the basic idea? The basic idea is that we need. So what am I trying to say? I'm trying to say something like, okay, I have something like x plus y less than 3, and I want to say, so let's call f of xy equals x plus y less than 3. Right, so that's defining a standard Julia function, and if I pass in, 1 and 2, then it will tell me that that is not satisfied because 1 plus 2 is equal to 3, and 3 is not less than 3. So for individual values, I can check whether this is satisfied. But what I need to draw these pictures is actually to be able to prove this for a whole region, right? I need to be able to prove this for any x in some range and any y in some range. So how could I do that? So suppose that x was somehow all real numbers between 0 and 1, and y was also the same thing, all real numbers between 0 and, let's say, 1.5. Between 0.5 and 1.5. So is it true that x plus y is less than 3? What does that even mean? Right, so let's call actually capital X to be like, this is a set, the set of all real numbers between those limits, and capital Y is that set. And so the question is, well, does it make sense to write capital X plus capital Y? What is that even going to mean? And so I'm actually going to define what that means. I'm going to define it to mean, oh, I'm going to take some little x and some little y, and this little x is going to be in x. And so this is like this. And, this is not Julia, right? This is maths. So this is how I'm going to define this sum of two sets. So in general, I'm going to define a kind of, for some like function of a single variable, I'll define f of the set capital X to be f of little x for all x in x. X in the set capital X. So that's the idea. So we're going to define these intervals. So I'm going to define a type that represents an interval like this. And then I'm going to define functions on that interval. And I'm going to make sure that I do it in such a way that it does what I want it to do. So in this case, I want to check that any x plus any y, where x is in big X and y is in big Y, satisfies that x plus y is less than 3. So hopefully it's clear. Yeah, this is Pluto. Hopefully it's clear how to do that in this particular case, which is that, well, any little x is less than 1. X is less than 1 for any x in this set that I define, and y is less than 1.5, or less than equal to, let's say, less than or equal to 1.5 for any y in y. And so what can I conclude? So therefore, x plus y is less than or equal to 1 plus 1.5, which is 2.5, for any x in x and y in y. And that is less than 3. So therefore, x plus y is less than 3 for any x in x and y in y. And so I've actually been able to prove, by hand, that these two sets satisfy that, adding anything in there together should give me something that's less than 3. And so, I can conclude that if I'm in that box in the plane between 0 and 1 and 0.5 and 1.5, everything in that box lies inside the set defined by this equation. Let's just go and look at what that equation looks like. And I can do that, using my tool. So x plus y less than 3. Hopefully you know that that looks like this. It's just a half plane. So it's like you have this line, and on one side you're in the set, and on the other side you're straight line. On one side you're in, and on the other side you're out. And then I'm saying that from 0 to 1 in x and 0 to 1.5 in y, this whole box here is inside the set. And indeed, that's right. And so that's basically, the basic idea behind intervals. So
Maybe just a little feedback. At least for me, there's a lag with the desktop sharing, like about 2-3 seconds.
Okay.
I hope it improves again, but just that you know.
Thanks. That's frustrating now. I can actually see that. Okay. Yeah. Thanks. Yeah. Okay. So now we need to actually do some coding, right? So that was like maths. How can we represent the maths in the code, in code? So, of course, the first thing that we need to do is define what we mean by an interval. So I'm going to call that a simple interval because I have my package that I'm going to load that has the actual interval definition. So what does that have in it? It has a sort of minimum value of the interval and a maximum value. And those are both going to be, for simplicity, float 64s. And so I can do something like x equals, so that defines a new type. I can do something like x equals simple interval 0 to 1, and that gives me a simple interval, and it converts automatically to floats for me. And then I can do y equals simple interval of 0.5 to 1.5. And then I can try and do, sorry, these should be capitals because they're sets. These represent sets, right? So I'm representing the set by just the endpoints. There's other ways to do it. For example, you could represent the set by the midpoint and the radius, the width. Okay, so now, of course, what I want to do is x plus y, and I try and do that in Julia, and what happens? It complains because it doesn't know how to add two simple intervals together. So it's my job as the author of this new package, right, to define that. So let's define how to add two intervals together. So I'm going to do base dot plus of x, which is a simple interval, and y, which is a simple interval. That's going to be a new simple interval. And what I'm going to do is take the minimum value in x and the minimum value in y. If I add those together, that gives me the smallest possible answer. And if I take the maximum values and add those together, that gives me the biggest possible answer. Okay, and so now I can do x plus y, and it works, and I get the answer. And now I'm going to check, I want to check, is the result less than 3? And so I could go and define less than, and etc. Right? So that's how I'm going to build up my world, right? Is that clear? So, so let's just do base dot less than of x, which is a simple interval, and y, which is some real number. How am I going to define that? Well, this interval I'm going to say is less than this real number if the upper value of the interval is less than the real number. And then I can actually check, is x plus y less than 3? And the answer is yes. Right? So you can see that I can start to build up my little interval arithmetic library like this. There's just one problem. What happens if I do x plus y, I get this interval, what is it? Is it true that x plus y is less than 2? So what should the answer be to that? Does anybody want to give an opinion? Is it true that x plus y is less than 2? So x plus y is this set of all real numbers between 0.5 and 2.5. Is it true that x plus y is less than 2? So I haven't actually, so I just defined less than like this. So of course I can ask Julia whether that's true, and it will say it is not true because of the way I defined it. But what should it actually return? Well, part of the interval, for part of the interval is true, and for part of the interval is not true. So in some sense, it should return both true and false. Yeah, thanks. So so this strange base dot colon plus is pretty annoying. Normally, I would do something like import base plus. That means that plus is a function that lives in Julia base, which is where all the main functions live in Julia. And then I could just write plus here, plus of x simple interval and y simple interval. But unfortunately, that does not work in Pluto. That's a Pluto restriction, not a Julia restriction. And so I have to write it like this. So that means like the function called plus that lives in base, this is how I'm going to define it. I can't put the parentheses. Yeah, I have to define it like that. It's a bit annoying to read. Yeah. Next. Yeah, so it's just referring to the standard function plus that lives in base. Okay, so this should actually return, ideally, should return sort of the set true and false at the same time, right? And so basically what we need is some kind of three-valued logic, true, false, and something else. True, false, and both, or true, false, and unknown. And so that is actually a big issue, and that has been a big issue in the package, and we haven't quite solved it. So there's another package called number intervals, which tries to solve this problem. Anyway, I don't want to spend too much time on it. I just want to point out that it's an issue that has to be thought about, because there are various packages that you might want to use with intervals that do checks like this, assuming that you have numbers, but when you have intervals, things can go wrong because of this. Okay, so I'm not going to go through and write for you all of these functions. Rather, I'm just going to show you that, it's already done, right? So let's load the package called Interval Arithmetic that we wrote together with Luis starting in 2014. And it's been developed since then, basically continuously. And then various people have come on board to help with it, especially Benoit Richard, Kolaru on GitHub, and Luca Ferranti that I already mentioned, and a few more GSOC students and a few other people have made nice contributions. So thanks to all the contributors who come from various different countries, etc. As open source should be. Of course, it's open source and it's MIT licensed, very liberal, etc. And because we're in Julia, it's super easy to load, right? So I'm in a Julia session. I just load in this package. You might need to install it. With Julia 1.7, that'll be automatic, or with Pluto, it's automatic, but it installs it for you. So now what can I do? I can say, okay, x. So I already used x, so I can't reuse x. So let's use little x. So I'm going to use this .1.2. That will define an object that's of this type interval and is parameterized by float64. So that means that inside this interval, there are float64s. I can also do like big of 1, big of 2. Let's call it x2. And then you can see there's 256 there. Means that I actually have big floats with 256 bits of precision inside my interval. So everything works with big float intervals as well. But it's much slower because big floats are slow. So you usually want to use float64s. Okay, so then I can say something like x plus x, is that less than 5? And it is. And x plus x, is that less than 3? And it says false, but that's pretty bad. It should really say this unknown or missing or three-valued logic thing. Anyways, but the arithmetic works, right? So x plus x itself gives me this interval from 2 to 4. So again, what does that mean? Well, let's define another one, y, which is 3 to 5. What does it mean to do x plus y? Again, it means take any value in this interval and any value in that interval and add them together. That will give me a range of possible results. And that range, I'm saying, goes from 4 to 7. So those are all the possible results of this calculation for any input value in this interval and any input value in that interval fall in this output interval. That is what interval arithmetic is doing for me. Okay. Great. So let's do, for example, 0.1, an interval of 0.1. That's another way to create an interval. And I can change how I output these intervals. So I'm going to do add format full. So now I can do interval of 0.1, and I can see exactly the floating point numbers that I'm using to represent this interval. So here I have an interval that has exactly 1 point in it, which is the floating point number 0.1. Right, I'm going to call that x3. So I can't reuse variable names in Pluto, which is a bit annoying sometimes. Anyway, whatever. So now I'm going to do interval of 0.3. That'll be my y. And now I'm going to add those together, x3 plus y3. What do I get? Maybe, okay, that wasn't quite what I wanted. Yeah, okay. So what you probably think just happened is that I have an interval containing the real number 0.1 and an interval containing the real number 0.3. And when I add them together, I should get an interval containing the real number 0.4. And the question is the real number 0.4 in this result? So let's look at x3 plus y3 and convert it to big floats. Okay, so in this case, it is actually, yeah, so that wasn't a good example. I thought this was going to be a good example. Okay, so that's because interval arithmetic was being kind of clever. So let's go back to my naive version. So let's make these simple intervals instead. So from 0.1 to 0.1, okay, let's just add a constructor or whatever. Just do it like this, 0.3 to 0.3. Now I'm going to add those things together. And of course, I get a simple interval from 0.4 to 0.4. So you might think this is just the point 0.4. But so this is where this floating point the floating point difficulties that somebody whose name I've forgotten was talking about, Christoph, was talking about come into play. So when I write 0.1 in Julia, it's not actually the real number 0.1. What it is a floating point number that is the closest floating point number to the true real number 1/10, right? So I can write it like that as a fraction, as a rational number in Julia. And when I convert that to a float 64, this is what I get out, but that is not the real number 0.1. That is this exact real number, which is the closest floating point number to 0.1, because floating point numbers only have 64 bits and they can only represent some particular subset of the real numbers. And then when I add that 0.1 and that 0.3, I get some floating point number 0.4. So the point is that I'm not actually doing the calculation that I thought I was trying to do. And so what I actually want to do is basically, I want to do something like this. Suppose I want to put in the true real number 1/10. Then I can do that using a rational number that is the exact 1/10 real number. And then I'm going to convert that into an interval. Okay, I need to convert it to, so we do actually currently have intervals of rational numbers in the system. I'm not sure if we really, that's not what I wanted. Okay, there we go. So what is it doing here? Basically, it's doing the following. It's doing interval of 1. That gives me a true interval from the true real number 1.0, which I can represent as a float, to 1.0. So it's just one single floating point number 1.0. And then I'm dividing that by 10. And when I divide that by 10, it does the calculation correctly in that it knows that these numbers are not representable exactly. And so it gives me a range of floating point numbers that are guaranteed to include the result, and which in this case is the true real number 1/10. Or 0.1. Okay, so how does it do that? So basically, so there's this let's say idea that is what Christoph was referring to, that how do I actually get interval arithmetic to work correctly so that it is guaranteed to contain the correct answer? And the answer is rounding. So what do I mean by that? So when I convert the real number 1/10 to a floating point number, it is going to pick, as I said, the closest floating point number. In this case, we saw that the closest floating point number is this one, which is just a bit above 1/10, right? It's a bit above 0.1. But I can actually ask instead for it to round it down. And if it rounds it down, it gives me the closest floating point number that is below this rational number. And that's what I have to do, basically. So when I'm converting to an interval, I'm going to take the closest floating point number below and the closest floating point number above. And that gives me a range of floating point numbers. That's an interval, right, that represents all real numbers between those two floating point numbers, and that is guaranteed to contain a true 1/10. And then when I do a calculation with that number, I actually have to do a calculation with every real number in that interval. In other words, I have to do interval arithmetic. So if I do x5 is, this interval that contains 1/10, and I make it into a sort of simple interval, whatever. Yeah. Then I'm basically, when I add these two together, I'm going to have to, when I add these floating point numbers, I have to guarantee that I'm doing the right thing, that I'm including all the possible results. And so what I actually have to end up doing is the following. So one simple way of implementing that, not necessarily the best, but the quickest, it's not going to give me the smallest interval possible, is the following. So I'm going to take the previous float of this and the lower bound and the next float of the upper bound. And that's actually going to, that's the way I can guarantee that I'm always going to contain all possible values in each floating point operation. So this is a pretty technical point. I don't want to labor it too much, but that's the answer to Christoph's question of how can we actually guarantee that we're getting the correct answer. We're always giving a range of values, an interval that is guaranteed to contain the true answer. And I always have to do this extra rounding to make sure that every operation contains the true result. Okay. So
a question from my side, actually.
Yeah.
Is there more difficulty to it if we go to 3 dimensions?
So actually, great question. So actually the answer is, okay, so how can we go to higher dimensions? Yeah. So in the interval arithmetic package, you can write things like this. So you can write \times, tab. That will replace this times with this cross, which usually means cross product, but we've reused it to mean Cartesian product. So I can do this nice, kind of mathematical expression, and what that gives me is an interval box object. So that represents the interval from 1 to 2 in the x direction and 3 to 4 in the y direction. So if I go back to format standard, and then I do this again, you'll see that it looks like this. So it's the interval 1 to 2 cross the interval 3 to 4, cross in the sense of Cartesian product. So it's, the set of all pairs x, y, such that x is in here and y is in here. Okay, so if I call that now capital X2, suppose I have a function that takes in a pair xy and does something like x squared minus 3 times y or something, right? That's a standard Julia function. Now I'm going to apply it to my interval box x2, which behaves like a vector, right? So it behaves like a tuple. Here I'm deconstructing this tuple. If you didn't know that you could write this in Julia, well, you can. So that enables me to call my function on a tuple like that, and it will sort of deconstruct the tuple into x and y values for you. So I can do that with my interval box, and that will deconstruct the interval box, and it will give x this value and y this value, and then it'll pass x and y into that function, and everything just works, and I get out a new interval. And so this interval, again, the point of interval arithmetic, what is the point? It has one job, and that job is to compute the range of possible output values, right? So what this is saying is, for any x in 1 to 2, and for any y in 3 to 4, in other words, for any y between 3 and 4, and any x between 1 and 2, when I calculate x squared minus 3y for those x and y's, for any x and y in those initial sets, the answer is always between minus 11 and minus 5. So that's a pretty, amazing thing that it can do, pretty strong thing that it can do. And it's really as easy as I was showing to do this. So, for example, plus turned out to be, pretty simple to code. Multiply, for example, turns out to be much more annoying to code, actually. You have to think much harder about how to do it, or, how do you do it most efficiently, but it's of course possible to do. And basically the problem comes because you have negative values and positive values, and they interact in a strange way when you multiply, because minus times minus can be plus, etc. So you have to really think quite hard about it. And square is its own thing as well that you have to treat in a special way, etc. Does that answer your question, Stefan? So basically the answer is the higher dimensions is actually no harder. It's just the same. Yeah, which is pretty amazing, pretty cool. Yeah.
Cool. Yeah. Thanks.
Yeah. So okay. So how can I use this stuff to do something useful? So sort of what are applications? By applications I mean like in scientific computing, right? So let's look at my favorite function ever, x squared minus 2. Okay, so that's a nice standard Julia function. And then I'm going to have an input, which I'm going to call up to x6 or something now. So I'm just renumbering these just because I can't reuse variable names. I'm going to look at the interval from 3 to 4. So I'm going to ask, for all x's in this input interval, what is the output? And so I can just do that easily, right? G of x6. And that will pass through this expression. So it'll calculate 3, 4, right? So what's it doing? It's doing 3, 4 all squared. What does that mean? That means take any x in here and square it. What do I get as a result? Well, I get the lowest possible value is 9, the highest possible value is 16. So it gives me the 9 to 16. And then I'm subtracting 2 from that interval. That means subtract 2 from everybody in the interval. And I get 7 to 14. So in particular, what is interesting about 7 to 14? Well, I can ask, is 0 in that set, right? And of course, we can see that the answer is no, 0 is not in that set. And because I'm in Julia, I can use these nice, so if I say at which on this expression, I can see which method is it calling. It's calling, in of x, which is a real number, and a, which is an interval. So this is defined in our package at this line. Okay, you can click on here. And that was a bad idea. Can't click on that. Okay, it's not going to. I can't look at that right now, but you can go and look at the definition and you can see exactly how it's defined, and it's defined as you would expect. Now this is an interval, and so how do I define when 0 is in an interval? Well, it's going to be something like in base.in of x in a in some x, which is a simple interval, is going to be true if x.min is less than or equal to a, which is less than or equal to x.max. And if I'm fancy, I can replace this with \LE, and it looks nicer. Right? So that's the definition for a simple interval. So if I have, is 0 in the simple interval from -3 to 3, the answer is yes. You can see that Julia just makes defining these things so nice because I can just define this, in operator in one line on a type that I've already defined, and then I can use this nice syntax immediately, etc. Julia just makes it so much nicer to do that than in many other languages. Okay, so yeah, so what was I saying? Yeah, so 0 is not in there. So what do I conclude? So conclusion, this function g does not have a root. A root is a place where the function hits 0, does not have a root in the interval that I put in the interval 3 to 4. So if you're finding roots, which is a really common problem in scientific computing, for example, I have a mirror here and I have a laser pointing here, and I want to see, does the laser hit the mirror? And the mirror is like some sphere or something, like ray tracing, basically. If you want to find, does this ray hit the does this fan blade hit this thing here in my fan? That is going to exactly be, can I solve this equation? Or can I find a root of a particular equation which turns out to be a quadratic equation, for example? So this is a very common thing to want to do in all kinds of applications. And you can see that we have just gained some information about this question, right? So usual methods for finding roots in numerical analysis that you're taught in a numerical analysis course, they're very clever and they're very, there's lots of clever ideas there, but they can never really tell you if the function has a root. That's not true. They might, it's hard to define methods that can really tell you, with some certainty if there is a root, and especially if you have found all of the roots of a particular function in a particular region. And intervals enable you to do exactly that. So I'm showing that G does not have a root in this interval. Of course, we know that G actually does have a root, right? It has a 0. That if I put the square root of 2 in here, then I get exactly 0 out. And so the square root of 2 is a root. And so actually, if I do G of 1 to 2, we know that the square root of 2 lies in that interval 1 to 2. I get out something that contains 0. But unfortunately, I cannot conclude anything from this information because what I haven't told you yet is that interval arithmetic has a big problem. What is that problem? Suppose I have the interval 0 to 1. Let's call it Z. 0 to 1. And then I ask, what is Z minus Z? So Z minus Z should be 0, right? For any real number Z, Z minus Z is 0. And so for any real number in this set, I should get 0 out. And so, when I do it for each real number in this set, I should get the set of just containing the number 0. But unfortunately, when I do this calculation, I do not get the set 0. So that's terrible. What's going on here is, so this is called, this has a name. This has a name, it's called the dependency problem. What's going on here is that it is, the way interval arithmetic works, this is the same as doing x minus y, where x is the interval 0, 1, and y is the interval 0, 1. And x and y are completely different variables. Right? So it cannot distinguish between when these variables are the same and when these variables are different. And so it has to give me the solution for when as if these variables were different. And so if these variables are different, indeed I can choose any x in that interval and any y in that interval. Then I can choose, I can choose 0 from the first one and 1 from the second one, and when I subtract them, I get -1. Or I can choose 1 from the first one and 0 from the second one, and when I subtract them, I get 1. And so, indeed, this is the range of possible values that I might get out of this calculation. So that's terrible, because that means that, so for example, if I have my input, which was called x6, and I have a new function h, which is x squared minus 2x, you see that x is appearing twice in this expression. Then it turns out that maybe not for that input, but there's an input that's something like -1 to 1. It turns out that this output is actually too big, right? So this function, maybe that's not a good example, -1 to 0 maybe. No, -1 to -0.5. I don't know. Anyway, it turns out that this will actually overestimate the range, overestimate the output value, the possible output values. So let me show you that graphically. So here's a function, this same function, x squared minus 2x. And we're looking at it over the region -2 to 2. And so what I'm doing is putting into interval arithmetic -2 to 2 as the input. And on the y-axis, again, I'm showing the output, right? So the output from -2 to 2 of this interval is, when I do this with interval arithmetic, turns out to be -4 to 8. And you can see that it's actually overestimating the true range. The true set of possible output values only goes from -1 to 8 or 7 or whatever it is. So I'm getting this excess, and that's due to this dependency problem that I have the same x, but it cannot realize that those are the same x. It's really frustrating. So of course there are various ways, various solutions that people have come up with, various, solutions that people have come up with that are called things like affine arithmetic and Taylor models, and we have implemented some of those. As I said, they're basically, the same kind of idea, but more complicated. So I'm not going to talk about them, but that there exist things that try and make this better. But basically, it's always a problem, and you have to deal with it. So how can we deal with it in this case? So basically, what happens is that this overestimate is coming from this. Effectively, it's always coming from this thing I just said, that minus sort of doesn't behave right. And the amount of overestimate is basically to do with the width of the interval that you're putting in, right? So if I reduce the size of the input intervals, then I'll reduce the overestimate in the output, hopefully, most of the time. So that's what I'm going to do here. So I'm actually going to, so one possible solution to this kind of problem is, oh dear. This is what comes of not actually running. What? That's a big shame. Oh my goodness.
It's using a range as the index.
Okay, well, let me just do it by hand. So, where are we? Yeah, so what I'm doing is going to load plots. So the nice thing is that if you have an interval box, let's call it B. Actually, I made one. What did I call it? There's 1 to 2 cross 3 to 4. I called it x2. So I can actually just plot x2. So x2 is an interval box, right? So plots.jl, of course, does not know anything about intervals. It doesn't know how to plot interval boxes. But fortunately, we have, if you know about plots and Julia, you'll know that there's this thing called a plot recipe system, which enables you to actually tell plots how to plot your own object. And so you see that what we've done is just told it, oh, to plot an interval box, you just plot a rectangle with some transparency that goes from here to here and here to here. So it now knows how to plot interval boxes, which is really nice. And of course, it knows how to plot functions, right? And the function is called h. So I can do plot h, and I can tell it where to plot from. So I'm going to plot from -3 with steps 0.01, and I'm going to plot h. And then on top of that, I'm going to plot this box, x2. Right, but that's not actually the box I want to plot, sorry. Which box do I want to plot? I want to pass in my interval x, some interval, right? Let's call it interval x10. I want to pass in the interval -1 to, what we're doing, -2 to 2, yeah. I want to pass in that interval, and the output y10 is going to be h of x10, and then I'm going to make a box called b10, which is the interval box given by the x in the x direction interval and the y direction, the y interval. I need to wrap all that in the beginning because I'm in Pluto, and that's the output, and now I'm going to plot that output, so that's called b10. And so hopefully this will, there we go. So that's the same plot, right, done by hand. So here's the function, and here's my overestimate from -2 to 2. You can see that it is indeed an overestimate. And so now, instead of doing that, what we're going to do is do the same thing, but we're going to split up the input set. So we're going to do -2 to 0 and the h of -2 to 0. And then I'm going to do the same thing from 0 to 2. And 0 to 2. So I'm just splitting up the input box. And of course, I need a bang here to add it to the previous plot. There we are. So you can see that what happened. So this used to go from -4, and now it's still going from -4. So that didn't really help. But basically now what I have to do is keep splitting up these boxes. So you can see that this one got the exact output range. That was okay. But this one did not. This one has the overestimate. And so what I need is sort of, okay, I'm going to split that up further. I'm going to do 0 to 1 and 1 to 2. So this is what that widget was supposed to do automatically, but I don't know why it's not working. And you can see that basically it starts to reduce the overestimate of the output. So as I split more and more, and it's a shame that that's not working because it's pretty to see. As you split more and more, you reduce the overestimate. That's a theorem under certain circumstances. And so you can basically, if I split this into 100 boxes, you would get just like I did in my very first demo that I showed, you would get a very good close approximation of the entire function with a very small amount of overestimate. And you can reduce that more and more by splitting up more and more. And you can split only in certain places, etc. Okay, so that's the point. And so you can see that basically what we can end up doing. Yeah, it's really a shame. Let me see if I can get that to work. I just don't know what the issue is. It has
some good news. The sync is again perfect. So yeah, the sync of the desktop sharing is, at least for me, again perfect. It's really quickly adapting.
Yeah, I'm not sure what's going on. I don't think I'm going to be able to fix it right now. Okay, sorry. So hopefully the idea is clear. Okay,
is it
so
double naming of the slider?
No, it's some problem with the actual coloring apparently, because it's complaining about interval. It's complaining about this array of color objects, and it's the wrong size. So I'm not going to be able to find that immediately. Okay, so by the way, I can also do, so previously I looked at, H3 to 4 or whatever, and I said, oh, 0 is not contained in there. No, I don't want H, I want my previous function, G. This G, which was x squared minus 2. I did G 3 to 4, and I got that, and 0 is not contained in that. But I can also take like a huge interval, 3 to 1,000, and I can see, oh, 0 is not contained in there either. And now I can take a really huge interval, like 3 to 1 E8, which is 10 to the power 8. It's not contained in there either. And actually, I can actually put int. So I can actually write here \infinity. So this is an infinite interval, right? 3 all the way to infinity. And I'm proving that when I apply my function to any value in that semi-infinite interval, I get something between 7 and infinity. In other words, again, 0 is not contained in that, right? If I can actually ask that, is 0 contained in that interval? It is not. So I have proved that this semi-infinite interval does not contain 0. In other words, there is no root of my function in that huge semi-infinite interval. And so you can see that I can actually start asking questions, in the best case, not always, about functions on the entire real line, which is pretty amazing. And I can basically exclude, infinite regions of semi-infinite regions of the real line, and then concentrate my attention on only those parts of the function where there may be roots. Could I check divergence of series with that? No, I don't think so. You have to no, that seems hard. Okay, nice question, by the way. Yeah, so what I wanted to say, okay, so basically, okay, so now I've been excluding roots. I proved there is no root there, there's no root there. But I can't so far say that there is root here, and that's due to this dependency problem that I was talking about, because that is giving me an overestimate. So even if my overestimate contains 0, that doesn't mean that the true function range contains 0. So what can I do to prove that there is a root? So in mathematics has an answer to that.
Maybe just a quick one in between. I'm not sure whether that was already answered. There's a question, could I check divergence of series with what you've just shown?
Yeah, I did answer that question.
Okay, thanks.
I don't think you can. No. I don't see how you would use this to check divergence of series. I think that's a more complicated problem. You would need some kind of, you can't do that just numerically is the point. You'd need some kind of symbolic reasoning, I think.
Okay. Yeah, perfect. Thanks.
Okay, so so what am I trying to say? Yeah, so how can I prove that there is a root, right? So I have this function that, between 1 and 2, this is the wrong function. Okay, whatever. Between 1 and 3, I know something about this function, which is that it's increasing. And there's a theorem, that says that if you start below 0, the intermediate value theorem, if you start below 0 and you end above 0 and you're increasing, then there must be somewhere where you are 0 in the middle. So we can actually use that. So how could we use that? So if we go back to our function g, what we need actually is the derivative of g that tells me whether something is increasing or not. And so I need another package, which is forward diff. And so forward diff also knows nothing about interval arithmetic. The people who wrote forward diff had no idea that interval arithmetic existed. Forward diff is a package for doing automatic differentiation. I'm not going to talk about how that works, but basically what I can do is a very neat idea, and it enables me to say I want to calculate the derivative of my function g on the input 3, and it will compute the derivative numerically. But the amazing thing is I can actually just put an interval in, and it will give me an interval out as well. And so what does this mean? It means for any x in this input interval, the derivative is contained somewhere between 6 and 8. So in particular, between 1 and 2, the derivative is contained between 2 and 4. So again, I can ask, well, is 0 in that set? And the answer is no, it's not. And that means that I've proved that my function is increasing in that set. And so since I know, I can compute on one end of the set is negative and on the other end of the set is positive, that means that I can use this theorem, the intermediate value theorem, if I'm getting the right name of the theorem. Mean value theorem, there are various different theorems that you can use. I can prove that somewhere in that region there is a unique 0, right? There is a unique root somewhere. And then in order to find it, I can start just like, I can do what I was saying before. I can sort of bisect this interval and say, okay, what about between 1 and 5? Between 1 and 1.5, and then between 1.5 and 2, and then just start splitting up, and I can exclude regions where I can prove, I can do like g of 1.5 to 2, that does not have 0, so I can exclude that from my root search, and g of 1 to 1.3, that does not have 0, so I can exclude that, and I kind of zero in on the root, and I can keep proving, oh yeah, there's a unique root there, there's a unique root there, there's a unique root there. So I can get as close to the root as you want. So this is what's called an approximation algorithm. And basically it's some kind of version of bisection. You might have seen bisection in a numerical analysis course, but now I'm doing bisection in a rigorous, guaranteed way. I'm saying I can guarantee that my only result in this set is in this region, and I can keep making that region, that interval, as smaller and smaller. Okay, so there's another package called interval root finding that puts all this together. And it uses a method, there are various different methods that you can use. Numerical methods that are based on intervals that can prove, in the best case, can prove that you have found the roots of your function. Okay, so the way you use it is to say basically roots of g between 1 and 4 or something, and it should give you a list of all the roots of g between 1 and 4. So in this case, we expect there only to be one root in that input region, and that did not work. What is going on? There we go. I think it might have been using a different function called roots. So here's the answer. It's saying that there is exactly one root. It's contained in this interval, and it has proved that there is a unique root in that interval. And it did that using this, using something like this derivative test. So in general, you can't use the derivative test. I see that there's a question. I'll answer it in a minute. Thanks. In general, you can't do this derivative test exactly like that. And so what happens is there is a version of the Newton method for finding roots. So I'll show you that in a minute. But there's firstly a question. What will happen in the case of jump discontinuity in functions? What will it show there? That's a really great question. So let's try that. So for example, there's a function called floor, okay, which gives me the integer which is below my input and as close to it as possible. So floor of 0.1 is 0.0, whereas floor of 1.1 is 1. And so this changes discontinuously at 1. So what if I do roots of the floor function between 0.2 and 1.2? That should tell me that there's a root at 1, or it should tell me that something happens at 1. Something strange is going to happen at 1, right? So I'm not sure I've ever actually tried this. It looks like it's behaving.
David, I think you need to use the interval root finding roots again.
Oh, yeah. Thanks. How do I interrupt this? Dear. But that's weird. I shouldn't need to use the interval root finding. Yeah, I don't know what's going on exactly, and I don't also know what interrupt. Okay, that seems to have maybe, yeah, that seems to have worked. Okay, let's try it. Interval root finding dot roots. So, yeah, I think it's getting stuck in an infinite loop. So, yeah, that was a great question, but it shouldn't do that. So you can specify what method to use. So let's use bisection, and you can specify a tolerance. And then what it does is this. This is a much better answer. That's pretty nasty. Oh, yeah. No, this is a very bad example because floor is actually equal to 0 in a lot of places, right? So this is a very, very nasty example. So that's what it's basically telling me, that there's some 0 maybe all the way along the interval. So that's terrible. Let's think of a better discontinuous function. This is embarrassing. Let's think of the example x plus floor, I guess. That's probably better. X goes to x plus floor of x. There's no roots, of course. Yeah, okay. That seems to be an example. Is that a good example? Oh dear. Can anybody give me give me an example of a function that is has a what am I trying to do? Discontinuous function, but it has a root. And what does that even mean? I mean, okay. Well, anyway, this seems to be the answer. So it will actually say that it gives me, apparently this has a root at 0, but it cannot prove that root is unique. Basically it cannot say what is happening at 0. It doesn't know what is happening, and what actually is happening is that it's discontinuous there, right? But it doesn't know that. I mean, it doesn't. But it can. It sort of knows that it doesn't know that. If you see what I mean. Yeah. So there are definitely various nasty cases, and I definitely can't guarantee that it can always get the nasty cases right. But for example, what about the function x goes to sine of 1 over x? Right. That's a very famous function. So that has an infinite number of roots near 0, and so I think that will go wrong as well in some nasty way. Anyway, you can definitely break the thing pretty easily. But what about if I do a nice example? So dot roots, this favorite example of mine, and we're going to do it from -10 to 10. And you can see that it actually finds all of the roots. So it's reporting 2 roots. One is plus square root of 2, one is minus square root of 2, and it can prove that both of those are unique. And in fact, I can even put minus infinity to infinity here. So it can actually prove that those are the only 2 roots in this special case, right? It's a pretty special function because it goes to infinity in a nice way or whatever. Well, it's actually because I don't have a dependency problem. Anyway, it can prove that there are exactly 2 roots in the entire real line, which is pretty amazing. And if you're very lucky, that will even work in higher dimensions. So you can actually use this function in higher dimensions too. So let's see if I can manage to get that to work. X to y goes to, so I actually have to use the static arrays package for that and do an S vector output, I think. Or maybe I could have used a normal vector actually. X squared minus 2 and y squared minus 2 plus y squared minus 2 and x minus y equals 0 or something. And this should be an interval box. And let's just do minus 10 to 10 with 2. Like, if you look at some of my other videos, I actually have sort of pretty examples where I show this working, and it's not working right now. I don't know what's going on. So this needs to be a vector function, right? It needs to return a vector output. Yeah, I don't know what's going on. Something is not working. Sorry. Anyway, it is possible to do it with in higher dimensions as well. So roots of higher dimensional functions. Okay, so how is this actually working? It uses a really nice algorithm called the interval Newton method. So I don't have the picture of the standard Newton method here, but I can show you how the interval Newton method works. Maybe is this actually working? Yeah. So basically, here's my input interval. Here's my function. I'm trying to find a root of it. So again, a root is where this function crosses 0, right? So it's actually here. But right now, I'm starting with this input interval, this whole thing. And what I'm doing is taking some point in there and taking f of that point. So evaluating the function there, that gives me this point here. And then what I'm doing is computing this derivative that I just showed you over the whole interval. That's what I'm showing with these gray lines. So I'm computing the derivative of this function using forward diff over the whole interval. And that gives me an interval, right? Which in this case is something like going from 0 to, I don't know, what is it, like 3 or 4 or something. And so these lines are straight lines with slopes taking all the values in this input interval, going from 0 to 4 or whatever it is. And then I take all of those and I intersect all of them with the x-axis. And that's what this red interval here is. And basically what this is using the mean value theorem now to say any root of the function must lie in this cone, this gray cone of these lines are defined in this way I just defined. And so I can just take the intersection with the x-axis, and any root of the function must lie inside there. And now I'm going to take the next step. So I'm going to start now from that input interval, and I'm going to do the same thing. So I'm going to take some point in the interval, take f of it, and calculate the derivative over this new interval and draw those lines, and then take the intersection of those lines. And you can see that very rapidly this process converges, and it converges indeed to the root of that function. Now, if there are more than one root, what does it do? Well, you can see that when I take this cone, it's now a double cone, and when I take the intersection of that cone with the x-axis, I actually get two intervals, two subintervals. So I'm excluding this region here, which is not in the intersection of the cone. And then, so at the next step, I actually have to take those two separate intervals and do the process on each of them separately. And each of them will converge to its own root. And so you can see that this is basically, okay, so I mean, there's a lot of maths to do to prove that this is correct, but not even that much maths, but some maths. But this is actually correct. So this will actually find all of the roots in the interval. Of course, if there's a finite number, and so you also have to avoid double roots where the curve just touches the x-axis. Those you cannot prove using this technique. Anyway, but if in the best circumstance, you can actually prove that you can find all roots of the function in this set. And that, again, extends to any number of dimensions in principle. The problem in higher dimensions is that basically what we're doing is that we're ending up bisecting in all of these different dimensions. And so you can have exponential complexity, and you just have too many boxes to deal with. So by the way, one of the things that I've been working on in the last couple of years is running all of these computations on the GPU, because these are highly parallelizable computations. And Julia's GPU capabilities are perfect. Not perfect, I mean, they're excellent for this particular purpose. Okay, so probably should wrap up. So let me just show you another nice algorithm, which is how do I do optimization with this, with interval arithmetic. So that's called a branch and bound or spatial branch and bound type method. So how does that work? So I want to find the global optimum, the global minimum of this function. So here's the function. And again, I'm doing the same kind of thing as before. I have my input interval here from -10 to whatever it is, 8, and then the output of interval arithmetic on the y-axis. And then what I'm doing is taking the midpoint of this box, and I'm evaluating the function there, and I'm saying, okay, the global minimum of this function must cannot lie above this line, right? Because I have a value of the function here, so the global minimum has to be below that or equal to that. Okay, so what I'm going to try and do during this algorithm is just, so there's this green dashed horizontal line that's marking the position which above which I have proved that I cannot have the global minimum, and I'm going to try and push that down as low as I can. So what I'm going to do is start bisecting again these boxes. So the red box is the box I'm looking at right now, and the blue boxes are in a kind of queue, and that will be processed later in the algorithm. So the first thing I do is evaluate at the midpoint of this box. So here's my new box, and here's the midpoint. I'm evaluating the function, and I see that the output is lower than the current upper bound, and so I can actually lower the upper bound following this arrow. Right? So at the next step, I've now lowered the upper bound, and then I split this box into two again. And so now I continue to do that. So here, for example, I evaluate the function at the midpoint. I see it's higher than where I currently am, so that doesn't give me any information. And so I just move on to the next box, and I split this box into two. And I carry on doing that until I find a box like this. What is this saying? It's saying I now have my upper bound of the global minimum is this horizontal line. And I have, using interval arithmetic, I can prove, so this is where interval arithmetic comes into optimization. I can prove that for any input in this horizontal box, the output lies above this global minimum upper bound. Therefore, the global minimum does not occur in this box, cannot occur in that box. And so I can remove it. I can just delete it from my list. So I can just throw it away. And I just carry on doing that. So every time I find a box where I can have proved that the output lies above the current global minimum upper bound, I throw it away. And I just keep on doing that. This is called the Morse-Kelbo algorithm. It's actually from the 70s. And you can see that what happens is I end up creating a cluster of boxes around each around each of these minima, right? And I kind of keep refining them. Keep making them smaller and smaller. And so I can kind of getting at what's called a cluster of boxes. So I can never actually reduce it to one single box using this technique. I would have to use something more sophisticated to do that. I actually end up getting more and more boxes as I make them smaller and smaller. But the interesting thing in this particular example is the following. As I keep on doing this algorithm, eventually I find over here, that I have evaluated a box which is below this current minimum. And so I move the minimum down, and now the minimum is actually below these local minima that I had previously found. And so it's just going to remove and delete all of those boxes around these local minima now. And so it's actually found the global minimum over this box, right? So now it's just going to make a cluster of boxes around that global minimum, and that's the kind of answer. It's just going to, and it has to stop at some point, right? It's going to stop again with some tolerance, some box size that I impose from the start. And so that's the basic, that's like the simplest possible global optimization algorithm using interval arithmetic. And the point is, again, that every step is guaranteed, right? It's guaranteed that all of these boxes lie above the global minimum. It's guaranteed, etc. And so this is really one of the only numerical methods where you can prove that you have found the global minimum. Right? Normally, people publish papers where they say, "Oh, we did some kind of heuristic algorithm and we found that a new putative global minimum, a new supposed global minimum for the function." But then somebody else might come along later and find a better one. And so this is the only way, really. There are a few kinds of algorithms that can do this, but in the end, most of them reduce to some kind of interval arithmetic. And often they don't even know that that's what they're doing, but effectively that's what they're doing. Anyway, so that's really, it's a really powerful set. As I said, it's one fundamental idea, which is that you can, have a set and you can evaluate a numerical function over that set and give bounds on the output set, the range of the function over that input. That's the single thing that interval arithmetic does. But then it has all of these amazing applications to problems that we actually want to solve.
There's another question.
Yeah.
Thank you, WD. Does that mean imply that applying this method of interval Newton does not face the, quote, problem limitation that Newton method usually is only available certain machine precision boundaries? Or will this always be the lower limit?
I'm not quite sure what you mean by that. So because I'm using interval arithmetic, basically everything that I handle is an interval. That interval has floating point boundaries, upper and lower bounds. So certainly there are some functions that, for example, like have just barely, basically almost touch the x-axis, touch and go slightly below the x-axis, but the amount that they go below the x-axis is 1e to the minus 20, or 10 to the minus 20, sorry. So I cannot really handle that with floating point arithmetic. Normal standard float 64s, I cannot handle that, and the interval Newton method cannot handle that either. But at least it will say, I don't know, right? It will give you a region where it says, there may be roots in here, but I don't know. But then what you can do, so I don't know if I can come up with a function like that. Let's say x goes to x squared minus 1e minus 20. Let's say, yeah. Interval root finding. Oh, what is going on? I'm in the wrong. Yeah. Interval root finding dot roots of the function that takes x to x squared minus 1e minus 20. And from minus 10 to 10 something. Yeah, so it has proved that there are no roots of this function outside this tiny interval. And inside that interval, it doesn't know what's happening. Okay, so that is better than the standard Newton method, which would, probably give you some answer and not, it wouldn't, you don't really know the standard Newton method doesn't have any kind of diagnostics that tell you what it's thinking, right? Whereas here, it just tells me that it doesn't know what's going on in that interval, but it has excluded everything else. But now, because I'm in Julia, I can do big here. So this is now going to be an interval of big floats, and so that interval is going to propagate through the entire computation. And now it's using big floats with the default precision, which is 256, and it's unknown because it has a default precision, default tolerance. I can change that default tolerance. I always forget how to do that. It goes like this, yeah. And now it proved that there's a unique root there and a unique root there on the other side. So, the code is written as usual in Julia in a sort of as generic a way as possible, so that so that you can use big floats inside your intervals, and the code for the Newton algorithm is exactly the same. I mean, there's just one piece of code, but now we're passing big floats through, and everything just works with big floats instead. And now you can, solve this problem pretty easily and quickly. But yeah, nice question. And the answer is, well, you can always use higher precision, which might be very slow, but at least we got the results. And in this particular case, it was actually quite fast. So the interval Newton method is like the standard Newton method in the sense that once you're close enough to a root, if it's a simple root, it will converge quadratically fast. So it will converge super fast. The problem is getting to, like a magnifying glass. So the problem is actually getting to that root in the first place. And the interval Newton method is nice because it will actually basically halve the width of the intervals it's looking at each time. So it's sort of bisecting in some way automatically. It's a very nice method. It's very impressive. So yeah, so maybe I should conclude and summarize. I'm happy to take more questions and show more things. So basically, this is a set of techniques that many people don't know about, even though these techniques are from the 60s, I mean, or even earlier, the ideas behind them. And there was even software from the 60s as well, of course. But, as people in the Julia community know, it's really hard to use software often, even, so I guess in Python, there are a few interval packages. There's one written, and they're probably easy to use. But, in Julia, just everything is sort of nicer. And Fortran, Fortran is super hard to use. Yeah, that's a very good example. So, yeah, of course, there were interval packages in Fortran in the 70s, and people were doing computations with them, and they're great. They're very, they're written by experts, and the experts who were inventing these methods and whatever, and so they were great achievements for the 70s, but they're just hard to use, right? Especially for a sort of more casual user who just wants to find a few roots of an equation. You don't really want to have to go and understand how this package works, etc. And so Julia just provides such a much nicer environment in every way to use these kind of methods and make them more accessible to more people, right? So I'm not saying that everybody should use intervals for everything, of course not, because adding two intervals is a lot slower than adding two floating point numbers, because floating point numbers are optimized for the hardware, etc. So if you're doing some kind of fluid dynamic simulation, you're not going to be wanting to use interval arithmetic. But if you're doing something where you need to find all the roots of a function, or you need to find you really need the global optimum, or you want to solve a differential equation in such a way that you can guarantee that the result is correct. For example, you're working on a nuclear reactor and you want to guarantee that your reactor doesn't explode. If you can model your nuclear reactor as a simple enough equation, which you probably can't, then you can use these kind of methods to guarantee that the result will never hit this danger zone, for example, right? So that's what I wanted to say. So if you're interested, as I said, there's quite a few resources now about these packages with links to there are various books that people have written about the theory of interval arithmetic, etc. You can look at my workshop for more details, where I kind of go through these examples in more detail, maybe, etc. Yeah. So thanks everybody for. Yeah, I wouldn't trust my code around nuclear reactors either. Good point. Yeah. But one of the ways to get more trust is to use more trustworthy methods, maybe. But yeah, equally, I can't really guarantee that my code works, right? So we do have a very extensive test suite that has been developed by other people, actually, and then we ported it to Julia, and so we make sure that every change passes all the tests, but that doesn't mean that the code is correct, right? It's very hard to make sure the code is correct. So there are various implementations. If you know COQ, this theorem proving environment, people have actually written interval packages inside those environments, and they can prove that their implementation is correct, and then you can explore code, etc. So but yeah, so I guess I don't really necessarily want to emphasize the correctness part. I think of intervals now as being a really nice way to compute with sets, right? I can just compute with everything in a set all at once and get the answer. You get some information about the whole set all at once, and that's just super powerful. So what I didn't talk about was actually I just realized was I kind of gave the idea of how these methods work that I showed right at the beginning, right? Basically, you can think of it intuitively as just being, is the box totally inside, or is it totally outside, or is not totally inside or outside? Those are the three colors. But actually, there's a much more interesting thing going on as well, which is that if I have a box like this one here that maybe you can see, I can actually find part of the box. I can kind of split up the box and find part of it which I can prove as inside and part which is outside, and then the rest I don't know. And so I didn't talk about that. That's called interval constraint propagation, and it's a really cool technique. I've given a few talks about it at JuliaCon, etc., so I probably won't go into the details, but basically it does this. So here's my input box, and this circle shows, is like the boundary of what's inside and what's outside, and here there's actually a way to turn a piece of an algebraic expression like this into an algorithm that that actually shrinks the box. So it shrinks it by removing parts that it can prove is outside the set, for example, and you get this new box. So you can really split a box into pieces which are good, pieces which are bad, and pieces which you don't know. And it's this very cool technique, which is basically sort of taking an expression and rewriting it into a piece of code that describes an algorithm that does this, called a contractor. So you can go and read more about that. Okay, so I'll probably wrap up there. Thanks again for your coming to the talk. I'm happy to take more questions. Thanks.
Also, big thanks from my side, David. Thanks for being here. And as you see, we're still 12 persons around, so a lot of interest. So also thank you, participants, for joining today. You have been, I think, a bit more than 20, around 20 at max. It's also a really nice number. A lot have been interested to join your talk, David.
Yeah. Thanks so much again, Stefan, for the invitation, and thanks everybody for coming, and happy to be in contact.
If there were some more questions, I think we still have some time. Or there is indeed one.
Yeah, is there a GitHub with these notebooks? Yeah, I was wondering what to do with notebooks. It's not some of this material is not really online yet, so maybe I should just make a GitHub and put everything there. Yeah. I think most of it is somewhere, but it's hard to find it all in one place. So yeah, I probably should just put it up in a new repo.
If it's ready, we can also share it on the meetup page and the discourse page for it, so that you can easily find it.
Yeah. Okay. Well, thanks a lot, everybody.
Yep. Thank you too.
Yeah.
And thanks to everyone for joining. Bye. Have a good day.
Thanks, you too.